We're going to talk about fractals. I am Kalle, this is Rafael, and this is Jonas. We're going to talk about a little bit of the theory. We talked a little bit about or Christian did talk a little bit about the theory yesterday at the non-linear dynamics course lecture. But we're not going to do a lot of that, but we're going to briefly just review some of the theory and then go on to the history. And then we're going to do a lot of examples, like where fractals are being used or where they appear in nature and this kind of stuff. So, what are fractals? The characteristic that everybody knows about fractals, the characteristic that they all have is the self-similarity and the scaling variance, that if you zoom in on a fractal, you can zoom in as much as you want and it will still look exactly the same. Nothing will change. For example, in this Koch snowflake, it just looks exactly the same. And then the other characteristic that they have is how the size scales. If you have a square and you increase the length of one side, then the area of the square increases by the side squared. If you have a cube and you increase the size of the cube increases as the side cubed. But if you have a fractal, the exponent 2 and 3, the exponent is not an integer, it's a fraction, and that's why it's called a fractal. And we actually derived this fractal exponent yesterday in the nonlinear dynamics course, so no need to do that again. Okay, so the history of fractals is basically like this, that Leibniz mentioned in the 17th century that there are lines that have fractal exponents. But he only knew about the lines, he didn't know about 2D dimensional structures or 3D dimensional structures. And nothing happened, or no one did any research on them for 200 years. In part because they were deemed mathematical monsters. And a lot of people doubted that they could exist because fractals also have this characteristic, that they are continuous everywhere, but they are differentiable nowhere. And at the time, mathematicians believed that a curve that is continuous has to be differentiable, except at a limited number of points. So, and mathematicians believed this until 1872, when Weierstrass published a paper on the Weierstrass function, and he showed that this function is, in fact, continuous everywhere, but not differentiable anywhere. And this sort of opened the door, I guess, to further research on this area. So, I mean, in the subsequent years, a lot of the most famous fractals were discovered and published. And one of these fractals is the counter set in 1883. The counter didn't actually draw this picture. He mentioned it in passing, but he analyzed this function as an abstract function in his research on mathematical topology. He came across it. The pattern is much older than Weierstrass. You can see on Egyptian columns from centuries back that they used this pattern, and they probably appreciated the recursive fractal nature of the pattern for its beauty, for its aesthetic qualities. But still, Cantor didn't see this as a visualization. The first one to actually use visualization to represent a fractal, or this type of visualization to represent a fractal, and to use it to discover a fractal, it was Koch, who is probably the most famous Swedish mathematician, because, well, there aren't many famous Swedish mathematicians, and this name is very familiar to a lot of people now because of the popularity of this fractal. He actually drew this picture and published the results. And if anything, it's a testament to where the research was at what stage. It was now at the stage where people were actively looking for this type of patterns, and so some other work published. This is by a Polish mathematician, Sierpiński, also extremely famous. Another example of a pattern that artists have used for centuries. So by no means a new pattern, but he was the first one to note the fractal qualities of this configuration, and I guess to derive the basic fractal properties of the pattern. Okay, and so the Julia set, which is something that I just included because it's a famous set and it's the precursor to the Mandelbrot set, which is this set. And yeah, there's this similarity. And it's pretty cool to visualize this set, but it's famous for a lot of reasons. But first I want to talk about Mandelbrot himself, who is sort of the giant in fractal research. He grew up in Poland, got displaced because of the Second World War. He was a Jew, moved to France, went into hiding, then moved to the United States. And this is a very great thing for fractal research that he did move to the United States, because in the 60s and 70s he had access to IBM computers that were state-of-the-art. And as you have realized, in order to, as you probably realized, this is to draw this kind of fractal graphics, you basically need a computer, because it's very time-consuming to draw these types of figures by hand. But he had, for the first time, a mathematician had a computer to investigate this type of patterns, and he made enormous progress. And not only did he find a lot of patterns, a lot of fractals like this, but he also started seeing them everywhere. He started seeing them in nature and started seeing application for them in technology. So, I mean, because for a long time, people had wanted to model nature with the theory that they had from before, and with the continuous and nicely behaved curves. But Mandelbrot sort of said that no, wait, a lightning is not a straight line. It has fractal properties, and the coastline of Britain, this is his famous paper that probably a lot of you know about. The coastline of Britain is best appreciated or approximated as a fractal. And yeah, started seeing it everywhere, and just summarized what everyone had done up to that point, wrote a very popular book on the subject, and really put focus and attention on the area. And I think he's still doing that today, but he's probably semi-retired, but he's still at it.
He died.
He died 2010, right? Yeah, okay, so he died, but he did it up to the end, I guess. To his last dying breath. So now we're going to talk about some of those applications that in nature and technology that came up in.
Yeah, so people try to model nature, but let's talk a little bit how nature models itself. And it's often been said that the Mother Nature is the best designer that ever was seen. And fractals can be thought as one of the design principles that she follows when putting things together. So, I'll try to show you a few examples of fractals and describe a little bit why they are in there, what's their purpose. And let's start maybe from two things. But fractals are extremely abundant in nature. We can see them everywhere. We can see them from the plants to electrical phenomena. It's a whole variety of different subjects that we can find them. And there are various reasons. Either is efficiency, either is structural strength of such fractals in use. The reasons are really various. Other statement is that in nature there are no infinite fractals. That we cannot see any fractal in nature that will have infinite behavior. They are always limited due to physical phenomena like construction of an atom or the smallest construction that, for example, plant or animal can produce. And one of the most known, the best visualization of fractal in nature is Romanesco broccoli. It is constructed from the buds, which will become flowers, but the fractal behavior of the bud is that we can see a logarithmic scale of the bud. And the bud is constructed from smaller buds in the logarithmic scale, and the smaller buds are also constructed from even smaller buds. There are a few steps, a few iterations of this logarithmic scale of buds on the buds on the buds. However, it is not infinite. Broccoli cannot make them too small. The reason for such fractal behavior here are probably two reasons. First one, that this is one of the most efficient ways to cover the area, and while these are flowers, broccoli needs a high chance to get pollinated, so he needs a large area, and this is one of the best ways. Then even a single pollinating molecule comes there, it's high chance that it will be successful, that the broccoli will catch it and it won't miss it between its buds. The other thing is that when broccoli is damaged and like single bud is going somewhere away, it still has chance to regrow because it has the flower of itself, and the important parts are together, and even one single bud can grow to the full plant. Another plant or group of plants that exhibit fractal behavior are trees. One of the famous fractal patterns that we can observe is a fractal tree, its name, and this is like huge approximation how the tree will grow. And the thing is that tree has a fractal behavior in its branches. When we see at the connecting point of two branches, it's not so easy to see if we simplify the situation on which branch are we. Is it very beginning, like the very bottom of the tree, or is it around the far end, like the one of the last branching points? Reason for that is that trees need to gather sunlight, and using fractals is one of the best ways to increase the area of the sunlight gathering space with relatively low energy consumption. Of course, a tree can grow every branch from the single point, creating one very single branch at the bottom and to the ground, and then branching to every direction and gathering sunlight from every point. However, this will consume a lot of energy because each branch would have to be constructed from the very beginning. And here we can tree can set up like really big branches which will cover the major of the area, but the spaces between the area that is covered, the area that is not covered, will be filled through smaller branches, and this is how the tree will gather the greatest amount of sunlight with relatively small use of energy. As we see, plants have some fractal behavior, but animals also can show us something. Seashells have a fractal nature since they are built by animals, and the shell is built from segments. When we cut off one segment and rotate a little bit shell, zoom in on it, then the shape of the shell becomes very similar or even identical to the previous one. And such behavior, we can see it's a fractal because whenever we can zoom infinitely, almost, because now infinity is in nature, but we can zoom and the shell will become the same. And the reason for that is that each segment of this shell will support the other segments. It's one reason. So the structure will be much stronger when they are supported by each other. Second reason is that animal needs to run only one shape, so it doesn't need to spend any energy or space in his brain to learn how to produce other shapes. So these segments will repeat because they are appropriate, they are efficient for the animal, they are strong enough, so there is no point to input any other shape, any other segment in this structure of the shell. And the size is varying because animal is growing in size, so its capabilities will increase in time as it grows larger. This is why it starts from the very small segment and goes into the larger ones, which will fit its body. Of course, one could say that why doesn't it start from the large segment and repeats? That simply would take too long, and animal could die in the process of creating even one segment. But animals, plants, even our body can be an example of the fractal behavior. Blood vessels in our body are the great example, because they exhibit similar behavior of fractals as trees. We can see that there are large veins which deliver a lot of blood, but we have to fill out the space, the volume between these large veins with the smaller ones. And here also, when we look at the branching points, we can go up from the very beginning of the vein. We can go up and see other branches. If we simplify the situation to the lines, for example, then it's not so obvious which is the very last branching point, which is the middle or the first one. And this is how we see the fractal behavior here. Not only living things, but also nature when creating coastlines, for example. There are two fractals here. One fractal is that it's a little bit illusion for our eye, because when we look from the far distance on the coastline, then it's very simple, it's not really detailed. We go closer, we look on the smaller area, but and the details are much visible now. But when we again focus on the on the smaller area in ratio to the bigger picture, again details are not so good. It's rather simple picture again. Let's zoom out once again. Again, details become very visible, and when we focus again on the small point, it's rather simple, and we can do it almost infinitely. The thing is that is our eye and our measurement systems doesn't have perfect resolution. It's limited. So when we go to the edge of the resolution, things get simplified. So if we go a little bit closer and look at the smaller area, our resolution is calculated again for the new area, and like something what was previously simple now becomes very detailed. But there are like if we focus again on small part, it's again very simple due to resolution limitation. Other fractal, which can be seen here, is also called coastline paradox, because when we calculate length of a coastline, when we take really large scale, for example, like really large unit, for example, for this Great Britain, and 200 kilometers, length of the coastline is really big. When we go a little bit with a little bit more detailed unit, half of it, 100 kilometers, the length increases, and if we go even further, length also increases. So we can go as small as we want, and the length will keep increasing. And we can do it almost infinitely up to minimal distances, plant length, but it's really hard to do that. But the length will still be increasing, and it's a process that almost never ends. Also, we can see that in fractal behavior in electrical phenomena. The electrical charge wants to discharge as fast as possible with as small resistance as possible, so through that as low distance which covers as possible. And fractal behavior is by itself one of the most efficient ways to do that, because as we can see again, we have branching nature as in trees or blood vessels. So when the charge is searching for the point where there will be a little bit lower resistance of the thing that he needs to discharge with, of the ground, for example, then he will go and search for it. And the greatest area that he's covering, because we cannot go through one point and discharge when the resistance of the other point is a little bit lower, so he will jump to the lower resistance. And when he's discharging at one point of the ground, then the resistance is growing, so he will go farther until he reaches something. So when the resistance is uniform through whole ground, as we can see on the right, he will go up to the end or up to he discharges. Lightnings during storm also exhibit these branching points because they are also searching for this lowest resistance, but in the air in 3D, so in three-dimensional space. So we can see then that they are branching, and there is no really point where we simplify that we can say this is the very end of the line. Yeah, if it reaches the ground, then we can see, but until it reaches the ground, we cannot really say that it's the last point, it's the beginning, it's the middle point. Another phenomena in nature is a crystal formation. We can see that crystals also exhibit fractal nature, fractal patterns through the branching. However, crystals are growing in 360 degrees rather than in only one direction, as do with blood vessels, trees, or lightnings. Crystals are growing through same conditions because they are really small, so the conditions aren't really changing around them, and they are growing in these all directions in one plane. This is because the construction of the molecules of water, for example, in this case, that construct the snowflake. And the branching points will be points where the surface tension will be the lowest, and the surface tension will increase in the corners of the branches. So we don't. This is why we don't see really the planes of the but rather the branches. So when the surface tension gets lower enough, far from the branch, we'll see next branch. And also from these branches, when they grow big, large enough, we'll see other branches growing from them. And this is a pattern that we will keep repeat until the crystal can form. So when it can, we will do this fractal pattern. And now, when we know the symbols, the examples in nature of the fractal patterns, we can move on to application of them in technology.
Okay, yeah, we have seen that fractal pictures look really attractive. For example, this is a fractal picture where the different parts are colored. This inspires, of course, artists, and also is a nice tool for the teachers to make their lectures more varied, and also attract maybe uninterested students to learn complicated math. Something similar to art is design of computer games. We see here two artificial landscapes created with fractals. The left one is a mountain scenery with a lake in front, and the right one is a top view of an island created with fractal code. And this finds application, for example, in flight simulators, strategic games, and and of course computer games and movies. Now, how to create these landscapes? I will explain you the midpoint displacement, which is, if we look at the 5 points, which represent the grid, I take the first one and the last one and displace them by a random number. Let's say this. Okay, then I take the middle point, take the mean value, and displace them with an decaying random number. So let's say it's now here. So then we get 2 more lines. And then we again use the midpoint, take the average, and displace it maybe in this way, and maybe here. And then if we do this a long time, you can see that the mountain like shape is produced. This is of course for one dimension, which becomes then two-dimensional. If we want to extend this to 3 dimensions, we have to have a way to update the grid points, and this is called this diamond square algorithm, where the red points are updated, and then the mean value is taken, and the next point is updated. And the key is that the change of the random number is decaying, so the structure gets smaller and smaller. If we look now, and there is a resulting plot of such an algorithm, we see on the left side that it's a really nice mountain-like landscape with rough rock formations, and on the right side there is a more smoother algorithm applied, which enlarges the lower frequencies and dilutes the higher frequencies, and therefore is a bit smoother than the left one. Now we want to discuss what are the advantages of using such production algorithm, or what are the disadvantages. The first advantage is that it's really easy to implement. You just take a grid and update the values following a simple algorithm with random numbers, and the results are pretty good for mountains and mountain landscapes. Of course, there's always a drawback. In this case, we did not specify in which direction the number goes, because if we would flip this upside down, it would again look like a mountain landscape. If we do this in our nature, it's of course not a mountain landscape, because we have valleys which are not spiky, and also there's erosion and water flow, and this has to be implemented if you want to make a realistic landscape, and this of course takes away a lot of computer time. And also it's based on random numbers, so you don't know which seed to take to create the landscape you want. So it's easy to create, but hard to control. Fractals are self-similar, and this could also be used to compress files, audios and pictures, where an algorithm could look for self-similarities in the picture and then produce a code how to organize the self-similar parts, and you don't have to know every pixel anymore, you just have to know the basic fractal and then apply it following the function you found. The advantage is that it works really good for nature pictures, and that it's really fast to decompress. A disadvantage is it takes of course time to find all the self-similarities. So a good application would be if you have a database and you want to open pictures really fast and good scale, then you could use it, but it takes long to produce the compressed file. With a similar argument, you can also resize pictures, where you apply a fractal code which learns the self-similarity of the picture, and then you zoom in and the fractal code reproduces, for example, the eye. So the eye in this case is from Lena. It's really sharp in comparison to a standard tool in Photoshop, the B-cubic sharper. This is to the fact that the fractals know the contours, and the code reproduces the shape, while the B-cubic sharper uses some averaging and averaging algorithm to produce these lines. But not only in computer science fractals are used, they also are inspiration for engineers and designers to produce technology devices. For example, on the left side we see an antenna based on Sierpinski triangle, where we see that it's where it works for small wavelengths up to really large wavelength. So the red one is large wavelengths, and the smallest orange one is the smallest wavelengths. So with one compact antenna, you could cover a large range of frequencies. In the middle, we see a cut through a cable for bridges. Bridges cable are made of wires, iron wires, or steel wires. Now you have to find a way how to organize them. The easiest way is to just take them and bundle them, but it turned out that it's the best if you organize them in a hexagon shape and twist them. So you take wires, you make a hexagon organization, twist them, and then you go iteratively with these new produced ropes, make a cable out of it, and then make a cable out of cables, and then you get this pattern, which is a fractal, but of course not infinitely. And the brightest picture is a fluid mixer, where you want to mix two fluids, for example in chemical industry, where you pump one fluid through this distributor, and the fluid mix without a large amount of energy. You don't have to mix it, or you don't have to boil it, so that it mixes. And this finds application in chemical industry, and by the way, reminds us of our lung system, where we have also this large amount covered. Now I want to conclude our talk. We have seen that fractals appear often in nature and are a good tool to describe it or mimic it in computer games. There are some applications I showed you. Of course there are more, and they can be an alternative to conventional algorithms and procedures, and maybe they will surprise us later in the future. Thank you for your attention, and now we hope that you have a nice discussion.
Okay, thank you very much. Just a couple of